So today, we're talking about a huge idea, AI models that can actually travel. Now, that might sound a little strange, but it's a concept that could completely reshape the future of global health. Let's jump right in. Okay, so picture this. A hospital in Boston builds this absolutely brilliant AI. It's fantastic at predicting cardiac arrest, and it's saving lives. But then, you take that exact same AI model, you bring it to a clinic in Vietnam, and it just completely falls flat. The predictions are totally useless. So what gives? Why does this powerful AI just break when it travels?
Well, it all comes down to this, the data gap. You see, the world's most powerful AI gets trained in places with just mountains of data. We're talking wealthy institutions in high-income countries. But the very places that could benefit the most from that AI often have the least amount of data to build their own models from the ground up.
So that leads to the big question, right? Do we just throw our hands up? Or is there a smarter way to do this? Turns out, the solution isn't to start over everywhere. It's to teach our existing powerful AI how to adapt.
Think about it like learning music, right? If you already know how to play the piano, you don't start from absolute zero when you decide to pick up a guitar. You already get music theory, you understand rhythm, you know what notes are. You just have to fine-tune your skills for that new instrument. Learn the specific chords and how to hold it.
And that, right there, is the big idea behind a technique called transfer learning. It's all about taking a model that's already an expert at one big thing and using it as a starting point, a head start, for a new but related task. You're not starting from scratch. You're starting from a place of deep knowledge.
And this really shows you the difference. The old way, training from scratch, is like trying to build a skyscraper one pebble at a time. It's incredibly slow, it's super expensive, and it needs a mind-boggling amount of data. Transfer learning, it's more like a rocket ship. It's way faster, much more efficient, and you need so much less new data to get a fantastic result.
Okay, so how does this transfer of knowledge actually happen inside the machine? Let's pop the hood for a second and see what's going on. It's basically a two-step dance. First, you have pre-training. This is where a giant model learns all the fundamental patterns from a huge general data set. For medical images, it's like learning to recognize the basic building blocks: edges, textures, simple shapes. Then comes phase two, fine-tuning. You take that already smart model and you adapt it using your smaller local data set. You teach it the specific details that matter for your new task. And what's cool is how flexible this technique is. It comes in a few different flavors. You can use it for different but related tasks, like taking a general image model and teaching it to spot a very specific disease. Or, and this is key, you can use it for the exact same task but in a new place with different data, which is exactly the Boston to Vietnam problem we started with. Now, this is absolutely crucial, especially when we're talking about privacy and security. When one of these models travels, the patient data stays put. It doesn't go anywhere. What gets transferred are the abstract patterns and features the AI has already learned. So the knowledge moves, not the sensitive information it learned from. All right, so enough with the theory. Let's see how this is playing out in the real world, because this isn't just some academic idea. It is having a huge impact on the ground right now. Remember that cardiac arrest model in Vietnam? When they first plugged it in, its performance score was 0.467. Now, to put that in perspective, a score of 0.5 is pure random chance, a coin flip. So this multi-million-dollar AI model was literally worse than just guessing. But then they applied transfer learning. They took that same model and just fine-tuned it with a little bit of local data. And that performance score, it skyrocketed to 0.807. I mean, that is an incredible leap, turning a useless model into a life-saving clinical tool. And this isn't a one-off. The applications are just popping up everywhere. We're seeing it in medical imaging, where these big pre-trained models are helping doctors and clinics with fewer resources analyze things like retinal scans and chest x-rays with amazing accuracy. It's also a huge deal for making AI fair. We know models can be biased if they're only trained on data from one group of people. Well, transfer learning lets us adapt that model so it works just as well for everyone, across different ethnic groups. And it's not just about images or demographics. It's breaking down language barriers, too. Models that understand health information in, say, English can be adapted to work perfectly in Spanish or Chinese without having to build a whole new model from scratch. And it's even helping on a massive national scale.
In Brazil, researchers are using this to adapt disease surveillance models to the country's unique health data, making predictions that are actually tailored to the local reality.
Okay, but we have to be realistic here. As amazing as all this sounds, transfer learning isn't some magic bullet that solves every problem. There are some very real risks we have to talk about.
The biggest one is something called negative transfer. This is basically when the old knowledge actually gets in the way and messes things up. If the original situation is just too different from the new one, like say a model trained on super high-tech digital x-rays is then used on old analog films, the transferred knowledge can actually make the model perform worse.
And that's not all. You've got other headaches to worry about too. Things like different equipment or just different ways of doing things in the clinic. There's also the risk of getting overconfident because it works well on a small local test set. And maybe the biggest question of all, when a shared model makes a mistake, who's on the hook? Who's responsible?
So when you pull back and look at the whole picture, what's the bottom line here? What's the big takeaway from all of this?
Well, it's pretty clear that transfer learning really is a game changer. Yes, it makes AI development cheaper and way faster, but its true power, the real magic, is that it acts as a bridge. It extends the incredible benefits of the AI revolution to communities that have until now been largely left out.
It gives us a powerful pathway to a more equitable future in global health. But that leaves us with one last, really important question to think about. This technology can be the bridge, but who exactly is responsible for building it?